Okay, so in the last lecture, we differentiated reactive power loads and reactive power sources through some examples. In the last example, we considered a pure capacitor connected to a source, an AC source like this. So if I have a pure capacitor, then if it is like this, then if I am measuring the reactive power using a var meter, the reading I would get is, we have already seen that the capacitor was delivering reactive power back to the source, and the reactive power was 3600 var or 3.6 kVAR. So this var meter would read minus 3600 var, showing that the reactive power is flowing from the capacitor to the generator. So the generator is now behaving like a reactive load, even though sometimes we prefer to call it a receiver of reactive power, which of course means the same thing, the reactive load. Okay, so a capacitive reactance always generates reactive power. Before this, we considered a circuit in which we had a pure reactance with capacitance. Then we removed the reactance. At the time of at the time when both the capacitance and reactance were there, the capacitance was delivering reactive power to the reactance, and the generator was not at all delivering any reactive power in that example, in that particular example, because we considered 4 ohms capacitance and 4 ohms reactance, inductive reactance. Now, let's see another example in which all the parameters R, L, and C are there. So we'll see the currents carried by each of the elements. So this is my generator. This is my resistor, which is 2 ohms, and I have a capacitor like this, which is minus 3.5 J. Then I have an inductor like this, 3J. Then again a resistor, which is 4 ohms, and this is my circuit. So I have a current like this, I have a current like this also. Okay, now here the two resistors absorb active power. I have R1 as 2 ohms and R2 as 4 ohms. So these two resistors absorb active power, which can be found by P equals I squared into R, which is equal to, how will I find it? Let this be, this current I will find as, this is 14 amps. Let it be 14 amps, and this be 20 amps. Then this is 16.12 amps. Okay, 16.12 amps. Now, if I want to find the active power, P equals I squared into R, which is equal to 14 squared into 4, right? 14 squared into 4 for this resistor, which is this is 14 squared into 4. If I want to find the total active power, then I have to add both the active power absorbed by both the resistors. So 14 squared into 4 plus 16.12 squared into 2, right, into 2, which will give me, this is 784 plus this is 520, which is equal to 1304 watts. So the 3 ohms resistor The 3 ohms reactor, this is the 3 ohms reactor. The 3 ohms reactor absorbs active power. So if I want to find that, QL equals I squared into XL, I have to take, which is equal to 14 squared again into 3, which is equal to 588 VAR. So that is a reactive power absorbed by this reactor. Now the 3.5 ohm capacitor, I have a 3.5 ohm capacitor. For this 3.5 ohm capacitor, I have QC, right, which is generated by the capacitor, which is equal to I squared into XC, which is equal to 20 squared into 3.5, which is equal to 1400 VAR. Now the RL and C in the circuit generates a net reactive power of, what is the net reactive power? So this is 1400, right, 1400. Then this one is 588, right, 588. So 1400 minus 588 is the net reactive power, which is equal to 812 VAR. 812 VAR. So this reactive power must be absorbed by the generator because there is a net positive reactive power. So this should be absorbed by the generator. All the elements are already over. All the elements which generate and absorb reactive power, those elements are already considered. Now the remaining reactive power in the circuit, this should be absorbed by the generator. Hence, as far as reactive power is concerned, the generator acts as a load, right? Reactive power load. The active power absorbed by the resistors must be supplied by the generator. Hence, it is a source of active power. So here, the generator acts as source of P, but load with respect to Q. Load with respect to Q. And the active power produced is 1304 watts. 1304 watts. Okay, so in this case, the AC generator is a source of active power and a receiver of reactive power. Now, if we want to combine active and reactive loads, then we move on to the term, we use the term apparent power. So now I am going to the next term, which is apparent power. Apparent power. So in that case, say I'm considering a circuit like this. Again, the source G, I'm having a resistor. This is a resistor, and this is a reactor. Say reactor. So I'm taking this as current IQ, this as current IP, and this as E. This as E, and this is current I. So current I is equal to root of IP squared plus IQ squared. Obviously, it's the vector sum of IP and IQ, where IP and IQ are 90 degrees. They are 90 degrees apart. Okay, so loads that absorb both active power P and reactive power Q may be considered to be made up of a resistance and an inductive reactance. It can be considered as capacitive reactance also, but here we have taken an example with inductive reactance. So here in this case, the resistor draws a current IP and the reactor draws a current IQ. The resistor is an active load while the reactor is a reactive load. Consequently, IP is in phase with E, right? IP is in phase with E, while IQ lags E by 90 degree, right? Because the voltage is same across both the elements as they are connected in parallel. So this will look like this is my E, this is my E, this is my IP, this is my IQ. So this is my I, this is theta. Okay. Now the resultant line current I, this one, lags the voltage by an angle theta, right? So here if we are connecting some meters to, so my source is like this, I am connecting 2 meters here and this is connected to a load. This I am considering as a load having both resistor and reactor. So this is my load. So this is P equals E into IP, right, which will give me watts, and this is my war meter. Okay, this is my watt meter and this is my war meter. So this Q equals E into IQ. Okay, so I am getting P like this, Q like this. So my direction is now like this only. So the active and reactive power components P and Q both flow in the same direction as per this circuit, right? If we connect an ammeter into the line, suppose if we connect an ammeter into the line to find the current, it will indicate a current of some I amperes, which is equal to this one, right? Which is equal to this one. Now we are concluding that or the power supplied to the load is equal to the total power supplied to the load, because this is considered as a load, right? It is equal to E into I, where I is the resultant current, watts. E into I, watts. But this is obviously incorrect, because in this case previously our circuits had either pure reactance or pure capacitance. Here if I multiplied the source voltage with the current, either I got reactive power or active power. But here my load contains both the elements, reactance and resistance. So from the source side, if I am looking from the source side and I am just multiplying the resultant current with the voltage, they should be vector products. It cannot be just multiplied. So the power is composed of an active component in watts and a reactive components in wars. For this reason, the product EI is called apparent power. Apparent power. So this is the very basic principle of apparent power. And the apparent power is normally expressed as S. It is neither in watts nor in wars, but in volt amperes, voltage into current. So volt amperes. Okay, now we will see the relationship between P, Q and S, which you might have already gone through in your basic courses. So the voltmeter indicates E, the ammeter indicates I, the watt meter indicates plus P watts. I am writing it as plus P watts, and my war meter indicates plus Q wars. So knowing that P and Q are positive, we know that the load absorbs both active and reactive power, which is measured by the war meter and the watt meter. Consequently, the line current I lags behind the E by an angle theta. The current I can be decomposed into two components. One is IP, another one is IQ. right? One is in phase and another is in quadrature. IQ is in quadrature and IP is in phase. So IP can be written as P by E, IQ can be written as Q by E. Right, now apparent power S equals EI, so I equals S by E. So this I is resultant. This is one component, this is another component. So this is how we take the relationship between active, reactive and apparent powers. Okay, now in this case again we'll just draw the phasor diagram to explain in a better way. So this is IP, this is IQ, this is resultant I, this is theta, right? So I squared equals IP squared plus IQ squared, right? So this can be written as from this these definitions, this equation can be rewritten as S by E the whole squared equals P by E the whole squared plus Q by E the whole squared, which is equal to, which implies S squared equals P squared plus Q squared. So this is the relation between apparent, active and reactive power. Now, if you want to find theta, which indirectly gives the power factor cos theta, I need to take tan inverse IQ by IP, right? IQ by IP. So, okay, IQ by IP. Because tan theta here equals IQ by IP. So theta equals tan inverse IQ by IP, or I can write as tan inverse Q by P equals theta. Okay. So now I'm going to apply this in an example. An alternating current motor absorbs 40 kilowatts. So it's a load, right? Electrical power is converted to mechanical power, or electrical energy is converted to mechanical energy, and the electrical power absorbed by the motor is 40 kilowatts, and the reactive power absorbed by the motor is 30 kVAR. If I want to find the apparent power, S equals root of P squared plus Q squared, directly you can substitute 40 and 30 here, you will get 50 kVA. Now another example we'll see. A wattmeter and warmeter are connected. A wattmeter and warmeter are connected to a 120 volt source. A wattmeter and a warmeter are connected to a 120 volt single phase line that feeds an AC motor. So I'm writing this as AC motor, and it indicates 1800 watts. This wattmeter indicates 1800 watts and the warmeter indicates 960 VAR. Now you are asked to calculate the in phase and quadrature components IP and IQ. IP and IQ you are asked to find. How will you find it? Your IP is equal to active power is 1800. So this is the active power component of current, active component of current, right? So 1800 divided by 120. What is this? P by E, right? P by E, which is equal to 15 amps. Now if you want to find IQ, this is 960 VAR divided by 120 volt, which is equal to 8 amps. From this you can find the line current. What is a line current? Here in this case, line current equals root of IP squared plus IQ squared, which is equal to root of 15 squared plus 8 squared. This is 15, this is 8, which is equal to 17 amps. So this is the resultant current. Now you can find the apparent power easily because the voltage is 120 volt and the resultant current is 17. So 120 into 17 will give you the apparent power. 120 into 17 will give you the apparent power, which is 2040 volt amps. Now if you want to find the phase angle between E and I, E is the reference, current is the resultant current. So that will give you theta. So theta equals tan inverse what? Q by P, which is equal to tan inverse, what is Q? Here Q is 960 divided by P is 1800, which is equal to 28.1 degrees. Okay. Now one more example. A voltmeter and ammeter connected to the inductive circuit. So in the previous problem, we have seen the connected meters were wattmeter and warmeter. Here I have voltmeter and ammeter. 140 volt is the reading of the voltmeter and 20 amps is the reading of the ammeter. Now if I want to find the apparent power, how will I get it? How will I get it? Directly I can multiply, right? 140 into 20, which will give you 2800 VA, which is equal to 2.8 kVA. Right. Now if I want to find the reactive power, Q equals, again, how will I find? EI, reactive power is EI, which is equal to 140 into 20 equals 2800 VAR. Right. Here I'll one more. See, if the source is like this, which is connected to a pure inductor. Okay, it's connected to a pure inductor. Okay, we assume that it is connected to a pure inductor. In that case, you can take Q equals E into I. So 140 into 20, which is 2800 VAR, which is 2.8 VAR. So if a warmeter was connected into the circuit, it would give a reading of 2800 VAR. But the active power here is 0 because there is no presence of active components here. It is only a reactive component. So if a wattmeter was connected into the circuit, it would read 0. It would read 0. So the apparent power is 2800 volt amps, but because the current is 90 degree out of phase with the voltage, it is equal to 2800 VAR. So both are same only in this case. So this is just to explain the concept. Okay, I know that these are basic things, but this is just to explain the flow of active and reactive power in a circuit. Now coming to the next term, which is power factor. Power factor. What is power factor? P by S. Active by apparent. The power factor of an alternating current device or a circuit is the ratio of the active power to the apparent power S. If I want to apply this in a circuit, I'll take like this. If the active power P can never exceed the apparent power, obviously, because apparent power is the resultant vector, right? The two components are active and reactive powers. So the active power P can never exceed the apparent power. It follows that the power factor can never be greater than unity, right? Power factor cannot be greater than unity. The power factor of a resistor is 100% because the apparent power it draws is equal to the, for a pure resistor, the apparent power it draws is equal to the active power. Similar to what we have seen in the last problem, it was a pure reactor. In that case, the apparent power was equivalent to the reactive power. If it is a pure resistor, the apparent power is equal to the active power itself. So 100%. So basically it's the measure of how much active power is utilized from the apparent power, right? If it is fully utilized, then it is 100%. So the effective utilization of active power from the apparent power, a kind of that, okay, in layman's language. It's not the actual definition. And the power factor, then what will be the power factor of an ideal coil having no resistance? There is no utilization of active power from the apparent power. Whatever is the apparent power is completely the reactive power. So it will be 0% if it is a pure reactance. So to conclude, the power factor of a circuit or device is simply a way of stating what fraction of its apparent power is real or active, right? In a single phase circuit, the power factor is a measure of the phase angle theta between the voltage and current. It can be defined in that way also. Okay, so basically power factor equals P by S equals EIP divided by EI. This is apparent, right? This is active, which is equal to IP by I, which is equal to cos theta from the previous figure. IP by I. Where is it? IP by I. Okay, which is equal to cos theta. So now we will apply this in a problem. Calculate the power factor of a motor again in the same example. Where was it? The motor we considered here. In this case, this is the motor. We are going to find the active and apparent power. So the apparent power was 2040. The active power was 1800 watts. So naturally, I should get the power factor as 1800 divided by 2040, which is equal to 0.882, or I can say like this, 88.2 lagging, or cos theta equals 0.882, theta equals 28.1 degree, which we have already found out here. Theta, right? We had already found out theta. Here, tan inverse Q by P. Tan inverse Q by P here, 28.1 degree. The same thing you can find here from power factor, from the perspective of power factor. Okay, so that is one thing. Now, say a single phase motor draws a current of 5 amps. A single phase motor draws a current of 5 amps from a 120 volt 60 hertz line. The power factor of the motor is given as 65%. Find the active power absorbed by the motor. How to find the active power absorbed by the motor? How will you find it? First, we will find the apparent power. What is the apparent power drawn by the motor in this case? SM equals apparent power drawn by the motor. Okay, E into I, which is equal to 120 volt is the source into 5 amps is the current drawn by the motor, which is equal to 600 volt amps. Now, if I want to find the active power, P, active power absorbed by the motor, PM, which is equal to SM into cos theta, which is equal to 600 into 0.65. 65% is the power factor, 0.65, which is equal to 390 watts. Now, what is my QM, which is equal to root of SM squared minus PM squared, because root of PM squared plus QM squared is equal to SM. From there, I get this. So root of 600 squared minus 390 squared, which is equal to 456 VAR. 456 VAR. Now I'm going one step ahead with the concept of power triangle. Power triangle. We will explain the concept of power triangle using a problem directly. I'll use a problem to explain the concept of power triangle. So a 50 microfarad capacitor is placed across the motor terminals. Capacitor is placed across the motor terminals. Motor means the motor we considered in the previous example. I'll use the data. I will list out the data here. Don't worry. Now you are asked to find the reactive power generated by the capacitor, active power absorbed by the motor, reactive power absorbed by the line, and the new line current. I line new, because now we have included a capacitor. So with this, what is the change? That is what they are asking. Now what is my capacitive reactance? 1 by 2 pi Fc. Right. F was 60 Hertz. Frequency was 60 Hertz. What is the capacitance? It is given in the question, which is 50 microfarad. So 1 divided by 2 pi into 60 into 50 into 10 raised to minus 6. 50 microfarad, which is equal to 53 ohms. So this is my Xc, which is equal to 53 ohms. Now, how will I find the current in the capacitor IC? This is equal to E by Xc. Right. So say the voltage across the motor, the voltage input to the motor is E, and the motor may consist of both inductive reactance and capacitive reactance. As of now, we are only interested in finding the current through the capacitor. So the input voltage divided by the capacitive reactance, which we have found, which is 53 ohms. If I substitute in the denominator, then I'll get 120 volt is the voltage divided by Xc. My Xc is 53, which gives me 2.26 amps. So this is the current through the capacitor. Now, how will I find the reactive power generated by the capacitor? Reactive power generated by the capacitor. That is Qc, which is equal to E into IQ. IQ is the reactive component of the current. E is 120. What is the reactive component of the current? Which is the current through the capacitor. Current through the capacitor is 2.26 amps. So 120 into 2.26 amps. I assume that there is no other. Whatever capacitor is there, I have lumped it and I am taking the value as 50 microfarad. So whatever current is flowing through that capacitor, that I squared into Xc will give me Qc, right? Or I can evaluate it by multiplying voltage into IQ. That is also another method, voltage into IQ, which will give me 271 VAR, because 120 into 2.26 amps. Now the motor continues to draw the same active power, because we assume that the load of the motor is not changed, but because of the capacitor, the reactive power has changed. Reactive power flow has changed. So what about PM? PM is the active power absorbed by the motor. What all are asked? Qc we have found. Then PM. What is PM? It is still the same. PM was earlier. What was the PM earlier? 390 watts, right? It is still the same, 390 watts. We have not changed the loading. The motor also draws the same reactive power as before because nothing has taken place to the change in its magnetic field. Consequently, your QM is equal to what? 456 VAR. QM is equal to 456 VAR. Now, where is the difference coming? Some amount of reactive power demand of the motor is locally supplied using a capacitor. That's the only difference. So in effect, the reactive power that is delivered by the source will be reduced, or the reactive power that is extracted from the source by the motor would be reduced. Partially it is being fed by the capacitor, right? So the motor draws 456 VAR from the line, but the capacitor furnishes 271 VAR to the same line, right? So the net reactive power drawn from the line, if I want to find the net reactive power drawn from the line, QL equals QM minus QC. Here line means source. Okay, there is no separate line and impedance given. Here line means source. So QL equals QM minus QC, which is the reactive power absorbed by the motor. Some part is compensated by the capacitor, remaining is taken from the line. So 456 minus 271, which is equal to 185 var. Now the active power drawn from the line is same, 390 watts itself, that we have already seen, 390 watts itself. What about the apparent power drawn from the line? You are asked to find the apparent power drawn from the line, specifically line. Okay, so the reactive power drawn from the line is 185, the active power drawn from the line is 390. So the apparent power is S equals 390 squared plus 185 squared, which is equal to 432 volt amps. Now what is a new line current? The voltage has not changed. What is your voltage? V equals 120 volt. Voltage has not changed, right? What is your apparent power now? 432 volt amps. So 432 divided by 120 will give you the new line current, which is 3.6 amps. Now what is your conclusion? Earlier your line current was, what was your line current earlier? Line current was 5 amps, right? 5 amps here, 5 amps. Now it has been dropped to 3.6 amps. So by placing the capacitor in parallel with the motor, there is a big improvement because the line current is smaller and the operation of the motor has not been changed because the motor is loaded by at the same level. It is taking the same load, but the current that is drawn from the source is reduced now. So what is the updated power factor of the line now? Cos phi L I am taking, which is equal to PL by SL, which is equal to 390 divided by 432. This is V, not VAR, this is VA, which is equal to 0.903 or 90.3%. So the power factor has improved. What was the earlier power factor? What was the earlier power factor? It was, let me see, 65% was the earlier power factor. Now it has been improved to 90.3%. So the power factor has improved. The reactive power is locally compensated by the capacitor or partially compensated by the capacitor, which is placed across the motor, and hence the current that is taken from the line is reduced. So this gives the idea of power triangle. What is the idea of power triangle here? Say I have the power triangle like this, power triangle like this. Okay, now my I'm using another color here. This is my QC. This is my QL. So this is the reactive power taken from the source, and this is the reactive power taken from the capacitor. This is equal to 271 VAR. This is equal to 185 VAR. Now the total reactive power is 456 VAR. This is the altitude of the right triangle. Now PM is unchanged. PM is the base of the right triangle, which is equal to 390 watts. My apparent power SM is equal to 600 VA. Right. Now, if I draw like this, I'll get here 25.5 degree. What is this 25.5 degree? My new power factor is 90.3%. Right, 90.3%, which is cos phi. So if I take cos inverse 90.3% or cos inverse 0.903, I will get 25.5 degree. 25.5 degree. So this 25.5 degree I am representing like this. Okay. Now, what is my SL? This is my SL from the line. What is that? This is SM. This is SL. What is SL? Here 432 VA. 432 VA. So this is what is a concept of power triangle. Now, one more case we'll see where a system is comprised of several loads, multiple loads. Okay, motors with different power factors and all. We'll take a short break and continue with the concept of active and reactive power. Thank you.